I said I would put together a helper video for homework number 9, problem 1, because it is, I don't think it's terribly difficult, but it might be a little overwhelmed. Some students might be overwhelmed. And I meant to do this sooner, so I apologize. But I guess better late than never, principle. So what I've done is, and the idea behind this, we want to do a Carnot engine using water. And one of our motivations for that is we have built into the vapor dome on a TS diagram of water, we have some constant temperature regions. Now, not right here, we would have to do some monkey business to keep this as constant temperature, but it's pretty easy to keep something as constant temperature in underneath the dome. So we kind of start out at these 2 points. We're up here at the high temperature, that's a completely liquid or saturated liquid right there, just on the verge of being steam. And then down here where we have a saturated gas right there, and we can move between them, going from 1 to 2 isothermally. Then so that's let me think about that. That's yeah, there's going to be heat in, and then we're going to extract work out. And there's still going to be some change in work all the way along here. But here's isentropic, come down to here, this expansion. And then we're going to have heat out that goes between 3 and 4. And then we're going to compress it from 4 to 1. I believe I got that all right. And what I'd like to do is find out what all these properties are, and then find what the change in heat and the change in work is through each of these: 1 to 2, 2 to 3, 3 to 4, 4 to 1, and then compare the efficiency I would get based on the net work divided by the heat in, and compare that to the basic the Carnot efficiency, which is going to be equal to 1 minus TL over TH. So let's go ahead and find that right away. I mean, this is the shortcut to doing all of this stuff. So that'll be 1 minus, and I decided to go from 200 to 300. In your homework, I think I go from 100 degrees to 250. All right, so this is basically, I'm just changing the numbers, and you should be able to mimic the thing that I'm doing. And so I want to make sure that we go from the low temperature is 200, we have to go plus 273 right here, and divide it by the high temperature, 300 plus 273, and we're going to end up getting, so what's that going to be? 473 divided by 573, boom, and subtract that 1. So we end up getting 17.45%. And that's the best efficiency that we could possibly do between these two temperature reservoirs. So, but let's go through this practice right here. So we're going to start out, we can find the values, and I don't know if it's necessary that I look all of these up, but let's do a few of them as we're coming through here, all right? So in this first part, number 1, we can find all of this as the F at this temperature right there. So we would go to our table B11 at, let's see, what is the temperature we say we're going to be at? Yeah, we're going to go, oh, look, I already highlighted all of these. So I'll unhighlight them. So we can do that as we go along. Well, we could just take a look at it. Okay. So we would have, well, first off, we know the pressure right there at, no, it should be at 300 degrees. I apologize, 300 degrees. So here you go, 300 degrees. So here's the pressure, and here's the, I don't think I asked for the volume, but this is the one that's the specific volume. We do want the internal energy. So the internal energy is one we're going to write down, 1,331.97 for the fluid. And all right, so let's see. I'm going to look at my I made an Excel spreadsheet here. I'll put this over my other screen to check this out. And so I'll write all those down in 1, and that's going to be a temperature. The temperature is 300, starting at 1, and the pressure as I mentioned, was 8,581. I'm going to leave the units off. The entropy, which we definitely care about, is going to be 3.253. 3.253. Let's check it out and see as we go along there. Let's see, next page for that, right? For the 300. There you go. And then I didn't get the enthalpy. I don't need the enthalpy in this one. I do need the internal energy, and that should be 1, 3. Yeah, there you go. 1, 3, 3, 1. So 1.3, 3. Not 1 point, but 1,000. Excuse me. 1,000. This is gonna be a great video. 3, 3. 1.97. I barely fit it in there. That wasn't very neat, is it? I guess I'm going to waste time by trying to fix this. 3, 3, 1.97. I can't round it down and get it. Okay. And then the X right there, we should just say it's 0, right? Because it's 0% steam. All right, so this is one maybe we want to wait for a little bit so we're going to jump over it, and we can find 3. All right, so 3 is going to be all the G properties at 200 degrees. So we already have that up, and did I miss it somewhere? I guess maybe I guess it's on this one right here too. All right, so there you go. So the pressure is going to be 1,553.8. We can round down some things. The internal energy is going to be, because it's gas right there, it's on the line, so it's going to be the 2595 point, I'll put it 3. And I'll make this is 100%. So 1 is going to be the X, and the last one we need is the right here, we need that. So that's going to be our 6.4322. Now, the other 2 points that we have onto this are going to be found by going isentropically from 3 to 2, right? We're actually moving from 2 to 3, but this needs to have the same entropy. So for this, we'll write this right here. He's going to be 6.4322, and then the same is true for 1 to 4. So that's going to be 3.2533. Now we need to look this up. Some things we should know on the 200, right there, 0.4, that should also be 200, right? And should have the same pressure as 3, so 1553.8. This one right here, this is going to be the 300, but we don't know anything else about here except we have these 2 pieces of information. We have this and this, so we know for sure that we're going to have, we can interpolate to find what the pressure is by looking for this, and we know this is going to be the superheated. We'll find this in a second. So this is really the first challenge, is to find these pieces of information right here. And once we have this, we can find that. Once we have interpolated this is just good information to have, but we will need to get interpolated for this. So this is really our goal in our mission into that. So let's see what we will do first. Let's go to our superheated and try to find a combination of 300 degrees and a 6.4322. All right. So there'll be a little bit of hunting for that. We can kind of guess where the range of the pressure is, but let's just take a look first. Okay. So we go to the superheated, and superheated, let's see. I already know what the answer is, so I think, there you go, I see a 3 right there, and you can see the entropy right here, that's too low. But as I'm going down in pressure, here's 3,000. Here's my 6.2. So when I'm looking for the 300 right there, where I have 6.432, and that's pretty close, and then that's pretty close. So actually, I just nailed it. This is the two pressures between which, so it's somewhere between 3,000 kPa, kilopascals, and 4,000 kilopascals. So we need to interpolate here to find the pressure between 3,000 and 4,000, and then also for the internal energy, right? So no, that's not the internal energy, that's the enthalpy. Here's the internal energy. So you need to interpolate between there and there based on the entropy, right? So I will write that. Let's see. Can we zoom in on this and get those values? Somehow that didn't work. Oh, okay, it's right down there. Okay, so I'll do a little bit of interpolation. We'll do the pressure one first, right? I won't do the actual calculation here. But let's see, the thing that we want to try to find, we want P2, would be good to know. And so we're starting out knowing 6.4322, and above that is going to be 3,000, and below it, or I say below it, it's actually above numerically, 4,000. And so we would say we have 6.5389, and then here we would have 6.3614. And if we do the interpolation, we would get that P2 is equal to 3,601. And that's just a good thing to know. 3,601. Good enough. Now we want to do that same interpolation, but now do it for internal energy. So here's our 6.4322, and I'll do it. Yeah, here, all this is the same. And you could do it actually with the pressure, but it's probably you know, a little round off error when it went from here to there, so there'd be another one to go from there to there, so keep it the same. So this is going to be U2. And above, or I should say below, it's going to be 2750.05, and here we're going to have 2725.3. I don't know if you can read that. It's very, very small in the video, but that's what that value is. And so, and when you interpolate the thing, you'll end up with a U2. I think I got that right. It's going to be 27,000, 27 something, 2,750.47. But you know, they're really, it's really more. Sorry, that's kilojoules per kilogram. Internal energy has a lot more dependence on temperature than it does on pressure. So you can see that it didn't really change all that much in between those two things. All right, so we can fill that out here. 2750.5, call it. Okay. Now, the next thing to do is to get this, and we're going to be in a mixed range. So the first thing to do is to go back to table B.1.1, the saturated temperature tables, and find out what the quality is going to be right here in that mix. So let's take a look, and that's going to be at 200 degrees. So we could have written some of this down while we were there before. Let's get this open up bigger so we can read it. And let's go back to saturated tables. And there it was. Okay. And we want entropy for 200. right there. So let's get him in there. And so let's see, our entropy, well, I should go back to this. Our entropy for a 0.4 should be 3.2533 at 200. And we could double check, and it should be, if everything was done correct. Yeah, it's in between there, right? So it's in between 2.33 and 6.432, right? Because we need 3.253. So we're going to write this down, that 2.3308, and write down the SFG. And so let's see if we get that. Okay, so what we're writing is S is equal to SF plus X. And I guess this is X4. I guess I'll make that 4. SFG. And so we will write down that it's 3.2533 equals, and SF, I have to look over here. I think it's 2.3308. 2.3308. And our X, whoops, plus, I need to put the plus sign in there. Plus X4, and then this is 4.1014. Great. And I'm going to say my X4 is therefore equal to 0.2249. And the next thing I want to do is now use that to find what the internal energy is going to be. And that's going to be back up here. So the internal energy is UF 850.64, UFG 1744.6. So we could go U4 is equal to, I'm not going to bother writing the equation down. We'll go 850.64 plus 0.2249, and then times the UFG, which was 1744.66. And so that should equal, where'd you go? I think it's 1,243.1 kilojoules per kilogram. All right, so now the rest of this, let me go to my cheat sheet, bring it over here, is going to be just the conservation of energy. Right, so we're going to well, first we do the heats, okay, and now the heats are going to come in only in two places, because there's no heat coming in or out between 2 and 3 or 1 and 4. It's isentropic, right, and it's the definition of the thing. But there will be heat between 1 and 2. So how much is the Q1 to 2? Well, it's going to be equal to the temperature in, remember, you need to be in Kelvin, times, so this would be, let's call this T1, times S2 minus S1. And it's directional. So you want to go larger number first between there in terms of the 2 and 1. That's the larger number, what I mean. So, so we have 273 plus our 300, and then that's going to be times 6.4322 minus 3.2533, right? So 6.4322 minus 3.2533. And we should get a positive number right here. And that will be the heat in kilojoules per kilogram, right? So let me, like I haven't actually written this down, so let me see where I can get that. Yeah. And I believe if I did that correctly, I should have gotten 1,822 kilojoules per kilogram. And the other place that we can get the heat, Q, is going to be from 3 to 4. 3 to 4. So 3 to 4, and let's call it just temperature 3, because the direction we're going though is 6, acid 6, S4 minus S3. So 273 plus 200, and then we're going to go S4, which is, I never wrote this down up in here. Should have. Should be 22.5%, and that U was supposed to be 1,243. So sorry about that. I got distracted. So I want S4. Where's S4? So 3.2533 minus. So it's really just reversing these two things, right? So because they were. So let's just say 3.2533 minus 6.4322. And so we're going to get a negative number, and that should be 1,504 kilojoules per kilogram. Now we could just get the work right now, but by subtracting this from that, and that should be the work out, right? This is the heat in, here's the heat rejected, the difference from the first law. But let's instead, let's use what we know about the first law on all 4 processes. This is my reason for making this problem. So let's see, the first one that I want to do is I guess just march through it. Where I go 1 to 2. So here's the conservation of energy equation right here, and we go going from 1 to 2. So 1 to 2. We would say that Q1 to, no, sorry. I like to write this other way. Please indulge me. U2 minus U1 is equal to Q1 to 2 minus work 1 to 2. So we can find what the work from 1 to 2 is going to be by taking Q1 to 2 and subtracting, see if I'm going to say this the right way. Yeah, you're going to subtract U2 and add U1. So we already have that. We already just got that a second ago. So 1,822. And now U2, we found that up above, is 2,750.5. So 2,750.5, and then we're going to add to it U1, which is 1,331.97. 1,331.97. And most normal people would have just gone ahead and said 1,332. I don't know why I did that. But anyway, our work between 1 and 2 is going to end up being, as a net, let me see, I did this in Excel like I said. The work is going to be 403. So here's 403. So, and it's positive, right? So that means that there's work going out. While heat is coming in, work is going out. That's some of the importance of doing this assignment. That's one is to keep track of all these signs. And then we go from 2 to 3. So we're marching through our thing. So we're going 2 to 3, and you know that it's isentropic, but let's write the first law down anyway, where we go U3 minus U2 to be equal Q 2 to 3 minus work 2 to 3. We know that that's 0 because it's isentropic. So what we've discovered is that the work from 2 to 3, let's keep the signs correct, is going to be negative U3 plus U2. Right? So U3 is 2,595. U2, as we used before, is 2,750. So that should be negative, sorry, negative. I didn't put, you can't see it anyway. 2,595.3 plus 2,750.5, and so we get a work between 2 and 3. It could be negative, by the way, and no, it's not. It's 155, positive 155.18 kilojoules per kilogram. All right, so just two more. And now we're going to go from conservation of energy and go from 3 to 4. And say U4 minus U3 is equal to Q 3 to 4 minus work 3 to 4. Right? And we already know, let's see, so I'll rewrite this out as the work from 3 to 4 is going to be equal to the Q 3 to 4 minus U4 plus U3. And we already have that 3 to 4, although it's negative. Remember, we found it before right here. It's negative 1,504. So 3, 4 equals negative 1,504, but we have a minus U4, which is 1,243. So 1,243, and then plus U3, which is that 2,595. 2,595.3, and we end up with a negative 88. Did I do that wrong? Let me see. Double check. Oh, I think no. This should be a negative. Excuse me. That should be the negative 151. 151.4 kilojoules per kilogram. And then the last one, we're going to go from 4 to 1. And so U1 minus U4 equals Q 4 to 1 minus work 4 to 1. And this is an isentropic thing, right? Going from 4 to 1. So we're going to, that's going to be 0. And so the 4 to 1 here is going to be a negative U1 plus U4. And we have that by going negative 1. So it's a negative 1,331 plus 1,000. Is that correct? Boy, I feel like it's wrong. We're going to go 4 to 1. So there, looks like it should be, let me just double check something. There. Oh, I see. Okay, all right. Huh. And did I do anything wrong? No, okay. I just want to see what my signs are going to be. This should be 1. So 3,000. Yeah. Okay. Yeah. Okay. I got it right. Okay. 31.97 plus 1, 2. Looks like a 4, 3. I think I got that right. So our net, or not our net, our work from 1 to 4 is a negative 88.915. That's a lot. I don't need that many sig figs, but I did it anyway. Kilojoules per kilogram. Now what we really want is our net work. So let's add all of these up. All right, so we got here on the first one, we got 403.0 and then we're going to add 155.18, and then add in the negative 151.4, and then add in the negative 88.92, call it. And what we find for our net should be 317.9 kilojoules per kilogram. But more importantly, we're going to use this for our net work divided by our Q in, which our Q in is going to be that 1 to 2, right? So this is our 317.9, and our Q in is 1,822. And if you do the grand total of this thing, drum roll please, 3.7.9, 1,822, boom, you get 17.45%. And that matches our Carnot efficiency. What we've done is we've walked all the way and quantified each step along the way of this process. I gotta tell you, I think this is an important thing to witness, to put together and to think through and imagine what's going through on each one of these processes, and to see the values and how they work together, no pun intended, but also to see where that eventually we have this network. And to see that we are having the simultaneous thing take place where we have heat transfer, and for instance in between 1 and 2, but we also have work, and we can see from the signs how they're coming in and how they're going out. So this was, hopefully you can just change the numbers up in this homework problem and still perhaps learn something from it. And so I've made a video as promised. Good night.